The purpose of this session is just to give you an idea about the course, what exactly we are going to cover in the course, and in which particular form we are going to cover. So I will just I will start just to give you a little bit idea about the things which we are going to cover, and then in between Aditya is going to update you like okay from the synthesis point of view. So this is our agenda, like introduction, which we I think we have done it pretty much. Then now we are going to discuss about the course structure. So so like the name itself is a synthesis and NST. So most of the people, they are confused like okay whether we are going to discuss only the ST and the front end side or the back end side. And when I was interacting with few of you, still I figure out like okay most of the people have a confusion. Like STA is uh, related to the backend side, and that's not has any important role in the front end side. So in my STA, which I usually take a standalone course, there also I have mentioned a couple of times, like STA nowadays, STA is from front end to back end everywhere. So like you can say wherever there is a net list, and then the STA is also there. So just from the course structure point of view, we will give you an idea about like, okay, where exactly the STA is there in the front and back end, how the timing and everything is important, the synthesis also, and the backend also. So we will just give you a very brief idea, just to give you an idea. Obviously, from the next week onward, when we are going to start the session, then we will help you out. We will explain you, basically, not the help you out. We will explain you in detail, like okay, the front and back end, how the things are going to happen. Same like timing in logic synthesis and where timing in a PD flow. So these two things we will discuss little bit, just to give in the same context, like okay, why we are talking about the timing. Timing constraint. A lot of few people, you have asked like okay, these constraints are going to be the block level or SOC level. Frankly speaking, when me and Aditya was discussing, so we were like, uh, as such, constraints are constraints. And if you have a good understanding about the constraints, so for you, it doesn't matter whether it is a block level constraint, SOC level constraint. So yes, we acknowledge that there are a couple of constraints which you cannot apply as a on a SOC level, or there are a couple of things which is not important for the block level. But as such, there are a lot of constraints which are those are common in a block level and SOC level. The difference is like how you're going to calculate it, and what should be your the methodology, or you can say okay, uh, from where those numbers are coming. So what we are going to cover it in this particular section, we will just give we will give you a little bit idea about how the constraints are placed. And Aditya, he created a very good slide just to help you out in terms of the whole SOC level and the block level, how the constraints are working together. And so today we will just give you a little bit an idea about that particular part. Then the last one, which is a synthesis timing optimization. So this is the basically the timing optimization. So today we will just give you a little bit idea about the synthesis timing optimization, because most of you are aware about the timing optimization on the backend side. Like if I will say backend timing optimization or the timing closer, so you know all those things, but few people, they are little bit confused about the what is the synthesis timing optimization. So we will give you little bit idea about those things. Apart from that, there are couple of other topics, so we are not going to touch those topics. We will just name it, and if any one of you have any question related to that, like okay, what exactly we are going to discuss in that topic, so feel free to ask any question. Then this is going to be like in a technical, and so our target is like maybe in another 45 minutes or 1 hour, we will give you a basic idea like okay, what exactly we are going to cover. And then class timings and other details, like I would say the non-technical, the class timing thing, the tool related things, and if there is something, any one of you have any concern or you just want to understand, like, okay, whether we are going to cover uh, a particular topic or that's we are going to discuss in another half an hour or so 45 minutes means then is going to be all up to you how many questions or how many queries you have asked. Yeah, so that's the agenda. Now this is our course structure. So the course structure, like we have divided everything in terms of the timing and synthesis. So now you can see this logic, synthesis, and ST. This is our course. So I just tried like, okay, just to give in a perspective, like, okay, what are the different timing related things and how things are uh, uh, binded with each other. That's a course section. So now here you can see very easily, like, okay, we are going to discuss the timing constraint, the block and SOC. Even the timing optimization, again, we are going to discuss on the both as block and SOC. But we didn't mention this particular part here because, like I said, it looks to me it's the same thing. Like if you know the timing optimization, so everyone should tell you at least the block level and SOC. It should be the same. Then there are input output files. So we are going to discuss in detail about each and every input and output files during the synthesis and ST process. And it is going to cover mostly all the backend files, even the front end files. Actually, I'm using the wrong approach. So it's not a backend or the front end files. It's just an input and output files. So in our design, whatever be the input and output files, we are going to discuss. So more focus is on the input files because if you have a very good understanding about the input files like .lib, SDC, SPEF, then wire load model, then the technology file in terms of the TLU plus file, and there are a couple of files which is specific to the tool and the stages, like so we will discuss that thing also. Output can be depending upon the flow, so maybe we will not be able to cover all the output, but yes, when it comes to the synthesis and STA, so we will cover those outputs. So don't expect like, okay, the output file which is maybe the related to the verification, we will discuss that particular part, but yes, related to uh, front end to back end, whatever be the output files, we will give you an idea about that thing. Delay models and the delay libraries. Yes, so this is the fundamental. This is the root of the timing. If you don't know the delay, what are the delay models? What are the different type of delays and how the tool usually do the calculation? What is the back end of that particular parts is very difficult for to understand the STA part. And on the basis of my experience, I'm just telling you, like, people know about STA from the timing closer setup and hold checks, and there are a couple of other checks. But the moment you will ask them, okay, what is happening back end of the tool, like, okay, how the tool is going to calculate, from the, let us suppose if I'm talking about NLDM libraries, how the calculation is going to happen, how the SPEF is going to, if SPEF, the tool is going to read the SPEF, how they are going to calculate the net delay. So those things, still a lot of people, they have confusion. So we are going to discuss that particular part, I would say, in the great detail. And same like in the delay calculation, like there are the tools have the different switches, and that particular switches how tool is going to calculate. So those things we will discuss. Then there are a couple of advanced timing concepts. So advanced timing concept is basically like AOCV, then the POCV or CRPR. So from the synopsis terminology like CRPR. So those things we will discuss. So that is going to help uh, you guys in terms of design perspective also. Now, when I'm talking about the design perspective, then obviously we have to discuss, and we are going to discuss also the little bit idea. We will give you the little bit idea about the PVD corners, RC corners, so, and when we are talking about MCMM, so that what is the meaning of the multi-mode, multi-corner. So those things we will cover in the advanced timing concepts, because these are the things which is going to confuse a lot of people, and they don't able to understand like, okay, how the changing the switches between these things is going to impact my STA or the synthesis or the PD flow. The reason we have capped that particular part, because so nowadays a lot of automation is there, especially in the PD side, and also in the synthesis side also there is a lot of automations. When I'm saying the automation, most of the companies, they have the make files, the targets, so you have to just run it those particular targets and through the make file, and the moment you will run those things, you will get the result. And then the things come like, okay, you have to if there are any failure, you have to you have to fix those things. But the problem is you don't know in which particular environment that problem is coming, and sometime because the lack of that particular part, uh, we just try hit and trial methods, like, okay, but just try, let's try this particular part. So we will discuss those particular part, we will cover those things. Fixing setup and hold, obviously when I'm talking about fixing setup and hold, then I'm going to cover the what is the setup time, hold time, how you are going to fix in the backend side and the front end side, and what are the different methods, and what is the meaning of the violation when we are talking about from the industry or the design perspective. Just by seeing the report, how you will able to figure out like, okay, this is the problem. And when I'm saying just by seeing the report, in the sense, all of you know very well, there is no step-by-step process in a debugging and in the fixing. So like there is nowhere it is written like there are these are the five rules. You have to just follow these five rules and you can fix all the issues. Because if let assume if that's possible, then um, we don't need engineers. We just need one person who can just who can automate that particular part, and things are going to be complete. So that that is going to be integrated in the tool itself. But there is no thumb rule, which is good. That's the reason we are working in VLSI industry. But still, there are a couple of guidelines. There are a couple of things which can help you to identify, like, okay, this may be a problem. So we are not saying like, okay, this is a problem, this may be a problem. So we will discuss that particular part. We will give you some tips also, like, okay, these are the things which you should follow. So those things we will discuss in fixing this timing closure method. So the all the boundaries one, we are not going to discuss today anything about this. So I just gave you the rough idea, like, okay, these are the things which we will cover in this particular course. Few of you may know about the timing, and few of you already the part of my timing classes. So you know, like, okay, till what depth I will go, and I will just cover those things. Then there is a two things like the timing constraint and timing optimization. So these two portion today, Aditya is just going to explain like how we are going to cover. But what I just want to give you an idea about from the timing perspective, the flow, how in the back end and the front end, and why and where the timing is important. And these things we are going to cover in a great detail. So I'm not going in much detail about the VLSI flow, but just to give you an idea, like, okay, what is the VLSI flow? So I'm sure like all of you know that uh, when the things is started, it started with the system specification. So someone just sitting at a higher management level, the architecture side, they are going to specify like, okay, I need this particular system. Like let us suppose the Qualcomm came up with a new featured phone. So the whosoever is going to decide, but first of all we are going to decide the system part, like, okay, this is a system specification, and on the basis of that we come up with the architectural design, and from that we come up with the we decide, like, we just break it and we come up with the like functional part, like, okay, this is a functional design, the logical side. So I'm sure like all of you understand very clearly like what is the meaning of the logical design. So the logical is basically whenever we are talking about a dot b b dot a plus b. So these are the logics. So with the help of those logics, you have to achieve a particular functionality. So that's a part of the functional design, the logic design. And once you are clear with those logics, then we do the circuit design. So you can also understand this particular flow, like in a college days, we usually talk about the FSM, finite state machine, and mostly what happened, there is the problem statement, and through the problem statement we first decide like, okay, what is the current state, second state, third state. So till this moment everything is a theoretical, and then we try to convert it into the logic in terms of the, with the help of the k map, and with the help of some excitation table, we usually come up with the logical equations, Boolean equations. So that's a logical design, I would say. And once that is done, then we convert into the circuit design. Like, okay, now there is a flip flop, there is an AND gate and AND gate. So that's a part of a circuit design. Once the circuit design is done, like, like, okay, there is going to be so many AND gate, NAND gate, OR gate, and this is the connection between them. That's after that, the important thing is how you're going to design it physically. So till the point, till the circuit designing point, everything is, you cannot visualize it like, ideally I would say, you cannot visualize it like where exactly a particular AND gate is going to be placed in a chip, and what is going to be the size of my chip. So those things you cannot visualize. You can say like, okay, I know on the basis of my experience, but as such, you cannot say like, okay, this is going to be at this particular coordinates. But in the physical design, we usually start with that particular approach, like we physically. So that's the reason it is a physical design. Physically, where exactly this AND gate we are going to place. One thing is very important between the circuit design, means the before the physical design, and before the physical design, if you have decided like, okay, they are going to be 10,000 AND gate, then done. During the physical design, we are not going to increase the AND gate, because the moment you're going to increase the AND gate, definitely is going to change certain functionality. It can change certain functionality. So nowadays, as such, ideally physical designer, they are not supposed to add any such type of logical gate in the design. And if they think like, okay, they have to add it because of a certain reason, then they have to go back and they have to check the circuit designer, like, okay, this is the thing. So now you can understand like, how the front end side, how that much is important before the physical design. Like everything, the people who are working in the front end side, they have to decide like, okay, this is my circuit, this is going to be implement on a particular chip. So that's a part of that's the importance of the circuit design. I will explain you like, okay, in a front end also, which is more important as per my understanding, my perspective. But this is a major difference between the front end and the back end. So most of the people, they confuse like, okay, what is the difference in the front end and the back end. So this is one of the major difference. Now after the physical design, obviously you have to do the physical verification and the sign off. So there are a lot of steps in the physical design, but you just do it. But there are a lot of machine tool involvement, there are a lot of human, they are going to interact, and a lot of things usually happen. So we have to do physical verification, and this physical verification in the sense whether it is meeting all the requirement, all the checks as per the foundry, we will just check that particular part. So after that, also in the physical verification, we will also check like whatever the front end people they did it, whether we are still following those things or not. Because the after the physical verification, the next step is the fabrication. So the fabrication is the foundry. So what the foundry is going to do, they will just fabricate. Don't think like, okay, fabrication based company TSMC will come back and they will say like, okay, you have designed it in a wrong way. So they don't know. So they just know like, okay, what is a layer and what is the coordinate of that particular layer. And they just do that particular part. But before that, whether your chip is going to work properly or not, that's everything you have to fix it and during the physical verification. You have to make sure like, okay, whether it is working correctly or not. So after the fabrication, is a standard thing like in a packaging and the testing. So there is again a testing part is there, and then the chip is there. So this is basically the complete the cycle, I would say, VLSI cycle. As an engineer, as a VLSI people, mostly we work between the functional design to physical verification. So this is a portion where we usually work. When it comes to the way we divide the front and the back end, so some portion of the architectural design also we just keep as a part of the front end itself. And the front end, there is a again there are a couple of stages like behavioral description, RTL description, so how you're going to write that particular design, then functional verification. So this is basically the once you are going to design, you have to uh, verify that particular part. Okay, so there is a question. Just ask one question. Like, okay, fabrication will check for the DRC railways. So, uh, yes, Jashwant. So they check it. Fabrication foundry people, they just check it for the DRC and LVS, but they will check and they will just tell you like, okay, these are the problems in your design from the DRC perspective, not the LVS perspective. Basically, from the DRC perspective, they will check because they have to design it. Certain things. Now, if that's on up to you, you want to overrule, you can overrule. You can say like, okay, I don't care. You just fabricate it. So they will fabricate accordingly. But they obviously they have to fabricate tomorrow. You should not come back and you should not say like, okay, this is something which you should have informed us. So that's the reason they usually do this DRC check at their end. Okay, so I was just talking about functional verification, like in the front end, whatever the functions or the logic you have designed, you came up, then we do the functional verification, and then logic synthesis. So this is a step which we are going to discuss in the next slide in a very great detail. So I'm just this is very important in the whole cycle, at least for this course point of view, like what is a logic synthesis. So we will discuss that particular part, and after that you will get a gate level net list, and then again you have to do a logic verification and testing. So this is our front end, I would say, the different profiles, also the spectrum, like what all different things we are doing in the front end side. When it comes to the back end, so just a single block, but it looks like a single block physical design, but there are a lot of activities we are doing in backend side, like partitioning, chip planning, placement, clock tree synthesis, signal routing, and the timing closure. So when I'm talking about all these partitioning, like, okay, this we are doing if we are talking about the hierarchical design. And most of the time nowadays, the design is so complex, and we want our design supposed to be complete within a 3 to 6 months. So without this, it's not possible. Like, okay, without partitioning your design, if you think you can just as a flat, you can you can design it. That's not possible in such a short time. So that's the reason we are doing partitioning. And once you do that particular part, obviously you have to do the certain chip planning also. So this, at least for the physical design perspective, I would say, like, you can as an analogy point of view, you can try and just see like, okay, how from the house planning, the whole house building planning, like how a particular society that build. So there are, let us suppose in a society there are 10 towers, and within that particular towers, how they are going to place, how they are going to build those towers. So you can if you want to understand your physical design perspective, you just always just keep that particular part in your mind. Like, okay, partitioning, that means now the moment I say, like, okay, there are 10 blocks, that means I did the partitioning. There is a clubhouse, there is a swimming pool, I did the partitioning. So that's the on the basis of the functionality, on the basis of your domains, like in a power domain or the clock domain, on the basis of the complexity of your design, you can do the partitioning. So the partitioning is all about that thing, how you're going to simplify your design. Chip planning, like where exactly you are going to place which particular block. So if so think in this way, like, okay, uh, the clubhouse you can place in the equal distance from all the towers. That is one of the configuration. The another configuration is just keep the clubhouse in the one corner of the society. And then for some flat so for some towers it can be just like in a 100 meter. For another one, it can be 1 kilometer, depending upon the size of your society. So it depends like how you want to plan your chip, how you want to plan your society. So that's a chip planning thing. So there are a lot of factors in the chip planning, like how you're going to communicate with the outside world, how the different blocks are communicating with each other, what are the different constraints you have. So those things come under the chip planning. So whenever we are going to discuss the physical design thing, which we are already planning, like, okay, the next month after this particular course we will start the PNR thing also. Then we will give you the uh, in detail description about everything. So that's the chip planning. The placement, again, how you're going to place it within a single tower, how you're going to place, or within a single flat, how you're going to place the different things like your sofa, like your dining table. So those things come under the placement. So in a chip, basically it's all about the standard cell placement. So where exactly you're going to place a standard cell. Now there are a lot of confusion between the people, like, okay, top level chip planning, top level placement versus the block level placement and block level chip planning. So frankly, guys, these are the things which if you will think in that perspective, it is always going to confuse you. So just remove that particular part, then it is going to help you out. So placement is placement, chip planning is chip planning. There can be one or two rules can be different when you're talking about the top level, block level, the SOC level, the block level, but apart from that, everything is as it is. Clock trace synthesis, about the clocks, how you're going to combine the clocks, connect the clock with the clock source with the different blocks or the different flip-flops. Signal routing is mostly connecting the different, or you can say converting a line or the wires into the physical wires. So that's signal routing. And the timing closer. So that's basically, remember here it is written that closer. So I'm not saying like the timing is something which we are going to do at this particular stage. So few of people, or a lot of people, they have they have things like this is a part of this is something we have to do at the last, in terms of at the end of the session, at the end of the whole design, the physical design, I would say. So that's not the thing, that's a sign of timing. But as such, the timing we are going to do at each and every stages. So uh, uh, the next slide, I'm going to discuss like in a PD also, like how the timing is important. Now the important thing is why timing in the logic synthesis, why we are talking about the logic synthesis. So for that, first you have to understand what is the logic synthesis, what exactly we are doing in the logic synthesis. So I'm just giving a rough idea about, like, okay, you have the RTL. So there is a team, they are developing the RTL. And so now this RTL is a like the whole design RTL we are talking about. But obviously whole design RTL is very difficult to write in a on a single file. So you have to divide the RTL. So you are going to do the partitioning of the RTL. The moment you're going to partition your RTL, at that particular time, you you need a you need something, so that people should understand, like, okay, how these two different RTLs are going to communicate with each other. So in the sense, let us suppose the output of one partition is going to is going to be used by the another partition. So now when I'm talking about the partition, let's see from the technical point of view, this partition is basically the block. So just to give you a very small idea so that you can visualize the thing. So let us suppose if this is your chip, and I just divided this particular chip in these two partitions. So this is, I'm saying this is a block. Now these first and the second chip is these blocks. Basically, from the chip and from the fabrication point of view, it's the same thing. Everything is a flat. So there is nothing like in a line or somewhere. But yes, from the designing point of view, from the engineer point of view, they are going to design these two blocks differently. Differently, not the differently, basically the separately. So maybe out of you, maybe Sonia is going to design the block one, and maybe Jaswant is going to design the block two. So when I'm saying they are going to design the block, individual block, and they're on PC and they're on area, then they need certain information, like whether I'm going to communicate uh, with each other or not. So like, what is my input? The input is available at t equals to 0 nanosecond, or it is going to available t equals to 5 nanosecond. So until unless you don't know at which particular time frame I'm going to receive these particular inputs, so it's very difficult for you to build a system which can work in each and every environment, or at least it is very difficult for you to build a system which you can easily integrate with the top level. So let us suppose there is a buffer here, and from here I'm as a input I'm going to give that 0 nanosecond. Now if you don't know, like, okay, I will get the input at this particular pin at 1 nanosecond, then you're going to assume it like, okay, at this particular place I'm going to get the input at 0 nanosecond, and you will design everything with respect to the 0 nanosecond like this. So here it is a 0 nanosecond, and so these are the two input pin, and these two input pin as such in your block, one at one pin, if I will say like, okay, A and the B, at one pin you will get data at 0 nanosecond, another pin you will get the data at 1 nanosecond. Now until unless you don't have this information, then your system is not going to work as you are expecting, like, okay, it should work. So who's going to give you this particular input, and which particular form people are going to give you this particular information? So these are basically the constraints. So these constraints we will talk, and this is something whenever you're going to do the partitioning or the block level, this is very important. And that's the reason it's mentioned here. The moment you're going to divide your RTL, or you're going to do your partitioning of your RTL, you have to develop constraint also. So that's important from the front end engineer point of view. Like, they should know, like, it's not only about just writing the RTLs. The important is also just writing the constraint, at least for your block. So if you are doing the partitioning, so from the top level person, if they are doing the partitioning, then they should have all these constraints. Like, okay, on the pin A, you will get data at 0 nanosecond, the pin B, you will get the data at 1 nanosecond. So at least this information I should provide you. And the way, or you can say the language, or we provide this information, that is itself is known as a constraint, because that become a constraint for your design. You are not free to design everything yourself. Now you have to keep these two inputs, these two information, and then you have to design. That means in some way I'm constraining your freedom, and that's a part of a constraint. So every person who's going to work on the RTL side, they should have a very good understanding about this constraint thing, because if they don't know, they will design, their design is going to be the wrong one. And if their design is wrong, it's going to be like I said, the physical design people, they are just going to physically place all the things. So that's the reason I'm saying it's a wide timing in the logic synthesis. Now I will tell you the what is the logic synthesis, but I think by now you are able to understand what is the constraint, why I'm talking about the RTL person should also know the constraint part. Now till the first three block is basically we are talking about there are there is a flat design, you divided the design, you write the constraint. Then the fourth block, this which is the RTL integration and constraint checking. Now I'm talking about like, okay, now you develop the RTL, you write the RTL, optimize RTL, and after that you're going to combine it. You're going to integrate that particular things. So that is the constraint integration and the RTL integration and the constraint checking. So this portion like RTL integration. So what all the things like, okay, they're going to be whatever is your output of this at this particular stage, that output is going to be your RTL netlist, and you will have there are in the RTL netlist you have the different blocks. Like I have mentioned, there are the n blocks. Similarly, you will have a constraint, and then there is going to be the top level constraint, the block level constraint. So obviously here the block level means the block level constraint of each and every RTL. So if there are n blocks, then there are going to be the n block level constraint, and they're going to be top level constraints. So this top level constraint in the sense how the different blocks are going to interact with the top level. So that's what I'm talking about, the top level and block level constraint. Just one question, like how can we decide the constraint, on what basis we assign some values to the pin and net? So that's Vishaki. This is something uh, is a part of the constraint writing. Like what are those factors on which you should decide or you should write your constraint? So until unless you, like I gave an example, 1 nanosecond or 0 nanosecond, on what basis you have defined it, because you know like there is a wire which is going to connect directly with your block, that means 0 nanosecond. There is a wire, there is a connection which is through a buffer. Now that particular buffer will have a 1 nanosecond delay, and the net delay you can see the stage delay, so that become a constraint for your that block, like okay, after 1 nanosecond. Now the question come, how you're going to do the designing. Are you going to do the design the top to bottom or the bottom to top? So if you're doing top to bottom, that means on the top level you know the buffer. If you know like okay, at this particular place buffer is there, then it is very easy for you to write the constraint, like okay, you know the constraint like in 0 nanosecond, the 1 nanosecond. But if you don't know the top level thing, like okay, whether there is going to be a buffer or not, then there are certain thumb rule, like okay, we will divide the whole timing numbers with the 40-60 ratio or the 70-30 ratio. So when I'm saying the timing numbers, that comes under the category of the timing budgeting. It's consider this in this particular way, like your your father, he gave you a 5,000 rupees as a pocket money for the whole month. Now you don't know what exactly is going to be your expenses, but anyways you're going to do certain budgeting. And similarly the timing budgeting we do in that particular way, we know that okay, within this particular time we have to finish our this task. Then on the basis of the our experience, on the basis of a certain thumb rule, we will just divide those 5,000 rupees, like okay, 10% I will say for emergency fund, then the 4,000 rupees, okay, let's think like okay, 2,000, 50% like 50% I'm going to save for my books and all other academic related thing, 50% for my food and related thing. So in this way you will come up like okay, this is my thumb rule. Now so industry, on the basis of their experience, they gave you a, on the basis of the technology, on the basis of the type of the design, they will give you certain thumb rules. So that thumb rule obviously going to be like from top to bottom, from higher management to the engineer. And if they are saying like okay, the thumb rule is a 60-40, like 40 you can consider as a outside the block, and the 60 you can consider as inside the block. So if you have a timing, if I'm talking about you have to finish a particular task with a 10 nanosecond, then you know, like, okay, for 4 nanosecond is going to be as a part of my outside the block, and 6 nanosecond is I can use it inside the block. So these things which I'm talking about, what is this timing related thing, and how the boundary is decided, how inside the boundary and outside the boundary, how you're going to do that particular budgeting, we will give you an idea during our session, like, okay, these are the things we usually do. This is a thumb rule we usually consider in our design. Great. So come back to this particular thing, like why timing. So like now you know, like an output, there are there are two outputs, the RTL netlist and the constraint. And in RTL netlist, if it is a flat, then there is no need of any constraint also, but it is not a flat design. There are a lot of blocks are there. Okay, so this is a portion. Now let's talk about, like, what is a logical synthesis and what is going to be happen in the logical synthesis. So now you have the RTL of all the blocks. Now what is the RTL is just like in a language. In a language you have mentioned, like, okay, A dot B. That means it is an AND gate. It looks like it's an AND gate, but how you're going to design it, how you're going to logically you're going to design it, that's something is a part of a logical synthesis. So when I'm saying how you're going to design it, like the AND gate can be a normal AND gate. So when I'm saying the AND gate, so just to give you an idea, if I will ask you, like, okay, you have to implement an AND gate, it's very easy for you. Just you can say, like, okay, this is my AND gate. Or maybe someone will come and they will say, like, okay, no, I'm going to design the AND functionality like this. Or maybe someone from you, they can say, like, okay, I want to design it something. So it's going to be A bar plus B bar, and it's going to be, yes, A dot B bar. Yeah. So in this way, so the same thing you can do it in a 3 different ways, and which one you should pick, and which one, what all your options, that's something we are going to decide in a logical synthesis. Apart from that, let us suppose you have decided, like, okay, you will go with the AND gate. In your standard cell library, there are going to be a lot of options, a lot of different type of AND gates. So the question come, which AND gate, whether it's supposed to be the 1x, 2x, 4x, 8x, who's going to decide it? You can do it later on also, but can, as a logic synthesis, when I'm placing my AND gate, if I will give you an idea, like, okay, the 4x is going to be good for my design, then that's something is going to help the physical design or other stage, like, okay, yes, I have to place the 4x. Similarly, the HVT and LVT, similarly, it's going to be the 2 input, 3 input. So you can do all those things in the logical synthesis, but on what basis you are going to do, or on what basis you are going to choose. So one of the reason, or you can say one of the factor, that is a timing. So because timing is nowadays very critical. So when I'm saying that, no one is ready to compromise with the timing. They are ready to compromise with the power up to a certain limit. They are ready to compromise with the area up to a certain limit, but none of us is ready to compromise with the timing. And you can think in this way, like, okay, making a call is just like a two-step process. Dial a number and click on a green button. That's all. The whatever the when I'm saying the button, it is like, in your smartphone, there's an icon, you just press it there. But we need this particular process as fast as possible. So that means we don't want to compromise with that particular thing. So what happen during the synthesis process? First, we translate all these A dot B into some unoptimized intermediate representation, and then come up with a first level of gate level netlist. So remember when I'm saying the gate level netlist, so the gate level netlist in the sense now we are talking about the gates, standard cell gates we are talking about. At this particular stage, now you are defining the gates. Uh, Before this, everything is as a you can say the equations. In the logic synthesis is a place where we convert my RTL, which is like an A dot B, and just map it with the technology library also. So because if you remember, like just few minutes back, a few seconds back, I have mentioned standard cell library. So standard cell library, when I'm talking about like on a particular technology node, there is a standard cell library. That means now you know the physical structure, the physical layout, you know the timing, you know the power, you know the area, everything you know about that AND gate. So the moment you're going to map your A dot B with respect to a particular AND gate, that means that's a place where you're in that stage where you're trying visualizing the size of your chip, the timing of your chip, and the area of your chip, or the tool can understand all these things. And that's the reason just in a logic synthesis stage we are saying logically optimization. Now an optimization is it with respect to the timing. That means now I want to optimize my netlist logically, considering timing as a part of my goal. Like okay, I have to optimize the timing, and then accordingly I will see like okay, which may I supposed to make certain changes in the net list, may I supposed to use some other combination of the logic gates. So that comes in the logical optimization. So like Tilak asked one question like okay, why the timing is important, why we are doing those analysis at this particular moment, like in the setup and hold checks, why we are doing at this particular place. That is the reason, because if there is a setup and hold violation at this particular stage itself, and that means you're choosing maybe you're choosing one wrong set of standard cells. Maybe your design itself is not going to be close when everything is ideal. Even then, if you are not able to fix your setup and hold violations, then how you're going to close it when you're going to implement in a physical design perspective? Is obviously the moment we are talking about the physical design, then a lot of other factors uh, become the part of this violations, like because of the manufacturing defects, all those manufacturing defects, the effects will come into the picture, the net delay come into the picture. There are a lot of like signal integrity related issues. Those things come into the picture in the in a physical design. So that's going to obviously increase the number of violations. So if your pre-layout design, or you can say the post-synthesis design itself having a problem in the setup and hold, and couple of timing problems are there, which is where we are considering most of the factors as an ideal factor. If you are having a problem at that particular moment, then obviously you cannot fix it in the post layout on the, or you can say the placement time or the physical design point of view. So that's a part of logical optimized logical synthesis, and that's the importance of the timing at this particular moment. In terms of technology mapping, I already explained you like okay how lib is going to play a very important role, and then we will get the optimized gate level netlist. That's a part of synthesis. And once you have a once you have a optimized gate level netlist, you will just pass it to the PD people, and like I have explained, like there are the separate stages. And here the important thing is from the timing perspective, because we are not going to discuss too much about the PD in this particular course, but yes, the timing we are going to discuss. So I just want to give an idea like okay, what are the different places and the stages there. The timing is important. Like these are the floor planning, design initialization. We do a lot of things after that. Just after the floor planning, we check timing, whether if it is meeting our criteria, maybe the margin or the numbers. Then we move to the pre-CTS flow, which is a placement. There we have a couple of steps, and then again we check it. The setup check, we do it, and if something is failing, we have to go back and we have to fix it. Now again, the same question: can I waive these many things at this particular stage? Yes, depending upon the process which is followed in your company. In a few companies, they are very strict. They don't want anything to be open at a particular stage. So they will ask like, okay, fix all the violations. There are a couple of companies, they say like, okay, within a particular margin, you can fix it and you can just move ahead. So this is just to give an idea, like, okay, at each and every stage we have the timing checks, and we have to do it. And sometime it is a part of a optimization. So if you are doing the things through the tool, so tool say optimizing, so I am optimizing my CTS, I am optimizing my placement as per the timing. So they are saying like a timing aware optimization. So that means you provide them certain timing numbers. On the basis of that, they try to optimize the placement, so that there are less number of violations after the placement. So that's that optimization word come at that particular place. When I'm seeing the timing closer or the timing fixing, that means after the placement stage which tool did it, and then after that you figure out like, okay, there are a couple of violations, and you close it manually. So when I'm saying the manually, in the sense, you are with the help of the separate commands, if you are fixing those things, that comes as a part of a timing closer or a timing fixing. So in one way, other way, optimization is something which tool is going to do, but in the backend, the tool is going to do the same thing, like, okay, fixing the timing just by couple of methods. Close and the timing closer or the timing fixings are the same thing, like fixing or fixing those violations with the help of certain commands or by some methods. So those methods are almost common methods, I would say. Like if I'm saying changing the location of a particular buffer or the cell, so even manually you can also do it, and the tool can also do it automatically. So we are going to discuss in this particular course what are those different methods and how the you're going to apply, and in which particular condition you're going to you should apply those methods. And in terms of like if I'm talking about the placement, like I can give you an example, like, okay, placement of a particular cell, you just change the placement of a particular cell. What are the advantage and what are the disadvantage? How it is going to affect your existing design in terms of maybe the power area, or maybe it you are expecting like, okay, your timing supposed to be fixed, but there is something else is happening, because of that your timing become worst. So what are those factors? We will discuss those things in a great detail. And that's the area where uh, I would say I always like to discuss as much as possible, because if you know those things, you can easily fix any timing violations. So even if it is a thousands of violations or just hundreds of violations, it doesn't matter. So as such, from the flow perspective, this is the thing, and the timing sign off is basically just to checking the sign off word. I'm sure like all of you know, like sign off in the sense everything is there. Now there is a checklist. You have to mark it green, 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 tick, 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 tick. So that's the sign off thing. And if there is any problem, then you have to go back, or you have to tell your implementation team like, okay, this is a problem, and you have to work with them like, okay, in this particular scenario, there is a problem. So that's a sign off thing. And then after that, the chip is ready. So I think by now you guys are clear like where timing in the PD flow and what exactly we are going to discuss from the timing perspective. Obviously, we are not going to discuss about the PD flow in detail, but at least I will give you a little bit idea about like, okay, in a CTS, what happened because of that particular thing, how the timing is going to change. Similarly, we have discussed about why timing in a synthesis side, why it is important. So I think that's portion is clear to you. Now there are two more things which we are going to cover, and I will say like Aditya can explain you very well about the timing constraints. What are the different things we are going to discuss in the timing constraints, and he's also going to cover the optimization part. Like, okay, what are the way we are going to teach you, or we are not the teach you. That's so it's like why the way we are going to deliver, and we are going to discuss with you in terms of the different timing constraint and timing optimization. Aditya, please.
Yeah, I'll request the
Yes, yes.
control. Perfect. So before we get into the content, as I'm listening to the discussion going on, I wanted to bring up 2 points, a little bit generic. One is a lot of people have a doubt in their mind. Am I audible clearly, everyone? If
Yes.
not, please let me know.
Yes, Aditya, we can hear
Okay,
you.
perfect. Sorry. So I'll start again. A lot of people usually have a doubt that why do we do such a course? Considering their courses, workshops, NPTEL, and a lot of things out there. So this is not a marketing pitch. This is more from the perspective of what distincts this thing. This came to my mind since here there was a question as to why should we do logic synthesis, and it was and why should we fix timing at logic synthesis? Very good question. So the idea behind this course in particular is not to teach you too much theory, but give you enough trade-off information. So engineering is all about trade-off. You need to understand that how the flow is supposed to run, what are all the knobs, where are all the issues. So you are able to make good decisions as an engineer rather than someone giving you a script and you run that. Our aim is you are able to actually make those scripts, or you are able to actually fix issues you find in those scripts, because never in your ever in your life will everything work out perfectly. If it can be done perfectly, then as Puneet already mentioned, someone can automate it and you don't have a job, right? So that's why you should that's the perspective you should take in that course. That's what I'm trying to get at, is you should learn the trade-off space. Okay, if we are doing this, what's going to happen with this? What are the pros? What are the cons? So stuff like that. In engineering, nothing is ever fixed. You can do anything. It's your decision, your company's decision, your manager's decision. You come to a negotiation, and that's what you should try to learn out of this course. Second point I want to make is, since there are a few BTech students in this session today, and Puneet is expecting a lot more to join during the course of the session, some of these things would be new to you. And we will implement two things. One is we'll try to give you doubt solving sessions. Second is we'll try to provide you some additional material so that you are able to follow. Because some of these things come as you gradually progress or pass out of BTech. So if something completely goes over your head, please ask then and there, or wait as you feel best. Okay. Then now with that background, what I'll do is I'll dive into the timing constraint part. And Puneet has already put a good perspective of why this is important, where all it is used pretty much everywhere across the design. You are supposed to somehow use these timing constraints because they are the backbone of how your timing analysis happens. Now, again, there is a lot of discussion about whether it's block level or a SOC level. From our perspective, they are more or less the same. We want to teach you, or we want to explain to you, how do you write a constraint and what does it mean? And then we'll show you the whole picture and we'll tell you all the different possibilities. So let me dive into it. For example, now this is a very simple block, and some of you already understand basic figures here, like this one in the center here is a flip-flop. And again, these orange ones are flip-flops, which are getting clock input, and then clock is just getting passed through the block. Obviously, there is no buffering for clock shown here. Then these are X and Y are input ports, E and F are output ports. These blue boxes or ellipses in the center, these are logic blocks. So when I say logic block, combinational logic blocks like AB, A plus B, ABC, something like that. A dot B dot C, A's or B's, any possible combination of logic. Now, typically, a big block which you're given for writing constraints is a combination of multiple such logic elements, combinational and sequential like flip-flops. Now, you are supposed to write constraints for these so that the tool is able to, first of all, synthesize a netlist. So then what happens is you try to write constraints. For constraints are something, as Puneet already mentioned, you're providing timing information. Now, what do we mean by timing information? The way digital logic usually works is you are given one clock cycle. From rising edge of the clock to the rising edge of the clock, you are supposed to do one operation or combination of operations. So you get some input here at X, you do an operation in this blue cloud, and when the rising edge of the clock happens, you're supposed to capture it in that flip-flop, in the first flip-flop. So we look at here, this is the first part. So some information came here at to that input port X. Within the first clock cycle itself, whatever there might have been the delay coming to this port X, there is a delay through this logic cloud, and then another rising edge came and you captured it. Then the next thing can be, from when this rising edge happened, you captured the information in this flop. Then this flop passed on that information to its output pin, and then the logic passed through this logic cloud and then reached the input of the next one. Within one next clock cycle, it should have again processed that information and get captured in the next flip-flop. Now, basically, the idea is to define it somehow in a language so that your tool is able to understand all these timing issues. That is your goal, writing a constraint. Okay. Now, what happens next is we have a block here where there is no flip-flop capturing anything. Now, how do we write a constraint for such a thing? There is just combinational logic here. So this is what I mean by block level constraint. There are a lot more block level constraints. I'll start getting into about it in the next slide. But to give you a picture, this is something like a hierarchy, not hierarchy, a simple picture depicting what do I mean when I say write a constraint. Defining all the timing paths somehow by giving some timing values, or defining what is the loading on your output, what is the loading on your input, stuff like that. So these are all the things we'll get into. Now, when we say SOC level, now I want to give you this picture. Now, what we had here before was a digital block, a simple digital block with a couple of flip-flops. It could have, same block can be now scaled to thousands of flip-flops or even 10,000, a lakh flip-flops, any possible scale. That would be our single digital design. In this example over here, what we are doing is we are taking two digital designs in the center over here. We'll try to explain some of the timing issues for which you will try to write your constraints. Okay. Now we have two over here. In the first, what we observe is there is a clock coming from clock A, and then in the bottom one there is a clock C. Then in the top one, we see it is getting fed by an analog block and you output to an analog block. When I say analog block, what I mean is none of it does not take any clock into it. Okay. Now we also see that the first digital block on the top here has some control data. When I say control data, we mean that these bits set by this control data are always static. They are never changing. In the bottom over here, we are saying there is a memory which is passing data information to this digital block at the bottom. The top block is also passing data to the bottom block. It is also passing data to another analog block. Then there is this digital block which is passing information to the bottom current digital design. And again, in turn, it passes information to the output digital block. Now, let's see what we do in the next slide to it. In the next slide, what I say is this clock A goes into a digital logic and outputs another clock, which is called clock B. This clock is driving this current digital design at the bottom, its input digital design and the memory, this clock B. Okay. Now, when we have such a big SOC level picture, which is actually quite a realistic picture for a real world problem, which we get in a mixed signal chip, we design such chips where you have multiple analog blocks, you have multiple digital blocks, you have memories, and you face all these timing issues. And the problem is you need to write constraints to define such things. Now, let's break it down into some simple problems. Let's see. The first thing is, you see the data provided by this analog block and its output is asynchronous to clock A. It does not care when or where the data is being supplied. So you need to know how to write a constraint for that. Second is the static control input data. So the input data here is static with respect to clock A. That is another thing which you should learn how to write a constraint for. Next, we see is these capacitors over here. So this is something which you will learn in the course of delay slides, which we will present, the delay module and the stat timing analysis module, that everything in your design is a capacitor somehow or the other. Then that capacitor adds delay to whatever you design. You need to take that into account every time you're writing a constraint. So that input-output loading is again written as a constraint. Now next we'll see is this thing. So we see for this bottom digital block, what we have is the input data to it is coming on clock B, but its output data is going out on clock C. We need to learn how to write a constraint. There are multiple clocks now feeding this single digital design. These clocks can be synchronous. They can have complex shapes, for example, not have 50% duty cycle. They can be mutually exclusive and a few other things actually. Then one more thing, we know, you notice we put a memory here and it is feeding a data into this block. The memory and the block are both running on clock B, but the block is also running on clock C. Now there can be multi-cycle paths. When I say multi-cycle path, what I mean is this memory may not be read by this digital design on every cycle. So this digital design might be expecting information passed to it from the memory every 10th cycle or every 5th cycle. Because when we do design, sometimes due to the latency issues in the memories, memories are not read every cycle. You do double data rate kind of things, or you do parallel implementation of reading the memory. You do a bunch of tricks. So you need, there are always multi-cycle paths associated from memories. So for things like those, what we have is we try to write multi-cycle constraints. So this is the overall picture which I want you guys to realize. When we make a big chip, we have so much of it going on. And when we say write a constraint, you need to know how to write a constraint for all of this. So here, at this point, I would like to take a small break because I put down a lot of information for you guys. Anyone have any issues?
For constraint, we are only considering timing constraint, not area and power constraint.
So area, that's a very good question. One, usually the area constraint is also there. We will try to specify it. It depends. The prime focus will be on timing constraints. Area constraints are usually out of hand to begin with. In a typical flow, what happens is, and it depends companies to companies, I'm just mentioning usual flow. You run the block through synthesis. Once it meets all the timing, then what the synthesis tool does is it tries to optimize the area without violating any timing constraints. So that it depends on how you set up the flow. It's in the synthesis setup flow. If you prioritize area, then it will optimize the area and it may leave some timing violations. Again, this is, as I said, very good question because this brings us to the trade-off. You can
Hello.
do same thing with the power. Yeah. Yes.
Yeah, good. Yeah, I have
Yeah.
a question.
Yeah.
Yeah, we'll consider all asynchronous paths as a false path in synchronous, right? We'll fix that in CDC, I
Yes.
think.
Yes, you're correct.
Yeah. Anyway, we can define those clocks as a false path, right? We won't able to
Uh,
capture the timing for asynchronous path.
we don't capture the timing for asynchronous. We usually try to maintain the loading and the
Yeah,
transition for them.
yeah.
So the
And
loading, yeah.
here I can see clock B and clock A are asynchronous with each other. No need to consider the
Clock
timing for
B,
those.
clock B and clock A are kind of synchronous since they are
Okay.
defined using a digital logic.
Mhm.
It's a very good point. I actually forgot to
Are they
write here
coming
that clock.
from? Are they coming from same PLL or generated
Clock A
within
and
the clock?
C. Clock A and
Yeah,
C. That
yeah,
so that that's why I left it as an open question. We will try to explain all those things.
yeah.
If they are coming from the same PLL, they are synchronous, but there will be uncertainty, jitter, skew associated
Mm,
with them. What
yeah,
are the margins? How do you specify those margins?
yeah.
Okay.
If my question is, if they are asynchronous, we won't write any constraint for that. Actually, we'll define those paths are false paths. Right?
Yeah, you're right. If they are asynchronous, but that may or may
Yes.
not be true. So it depends. You try to specify clock domain crossing. What's
Hmm.
the time delay between the two timing logic cones? So stuff like that. So,
Okay.
but you're right. If it is asynchronous, then you try to just define it as a false path. But that is only a very small part of what we are trying to
Okay.
say.
Okay.
There are a bunch of other combinations possible.
Hmm.
Okay, but a very good question. Any other thing anyone wants to comment here? One thing I want to mention is we will try to give you some assignments on how to write these complex constraints and also explain them in the class. So that's one of the major goals for you to realize how to write these. Okay, next.
I have one question.
Sure.
I just want to understand the differentiation between when we call a design to be a synchronous design and a design to be an asynchronous design. So by the virtue of what classifies them to be an asynchronous design or a synchronous design? And then when we have to define constraints, like in my constraints, I see many of the data checks which are kind of defined at the CDC crossings, right? So we kind of set a false path or a multi-cycle path on them. So
Yeah.
with respect to the clocks and the design itself, I just want to understand what the jargon means in the first place.
Okay, so synchronous is, so I think Tilak was already mentioning this. Synchronous is usually the clock source is the same. Again, I might be oversimplifying a few things. We can get into it in more detail. But to begin with, very simply, think you are being supplied from the same clock, but your frequency is different. So for example, this clock A on the top, think of it as a 1 gigahertz clock coming from the source, which is same as the clock C source, but this clock C is running at 500 megahertz. Now, this clock A repeats itself after every 1 nanosecond, but this clock C repeats itself, its period is 2 nanosecond. They are both synchronous to each other, but there might be some delay which is different between clock A and clock C. So reaching different digital design blocks, there is a clock delay associated with them, which is different. Second, their noise on them might be different, which adds different uncertainties to them. So then you are supposed to write clock domain crossings for synchronous and done using FIFOs. And then you can also do clock domain crossings for asynchronous. When we say asynchronous, then it means that two domains have no timing relationship between them at all. So clock A is a 1 nanosecond repeated period clock, and clock C is some 500 megahertz clock, but there is no timing relationship between the two. This is, we will get, when I say no timing relationship, they are not driven by the same source. So in phase, they can be as far apart as possible, or they can be shifting. They're not driven by the same thing, so you cannot say any particular relationship between the two.
So my question was, so by the virtue of which that is what they are asynchronous to each other, right? If they're not from the same source.
Yes, that is one thing. The other thing can be, for example, this analog block. Now, in this analog block, this analog block is supplying the information of this data to this digital design as and when it lights. So all these data pins are asynchronous to this clock A. It does not, this clock A and this digital design does not know when this data will be provided by this analog block and when will the next analog block be reading the data. You understand this? So from the perspective of this digital design and this clock A, these are asynchronous data.
Okay. Yeah.
So just to add, Aditya. So same thing. I'm just trying to put in a different way, in a maybe other way. So if in a particular block, I would say, Landita, if you can figure out any relationship, okay, then you can say like, okay, you can design your circuit and you can synchronize your circuit or the different components of your circuit with respect to those two clocks, because you figure out that, okay, there is a relationship between those two clock, and that can be like in a time period or all those things. So from the tool perspective, if you are saying like a clock A and a clock B, they are starting at the same time and the same time period, or maybe the double the time period. That means by providing this information, you're telling the tool like, okay, these two clocks, there is a relationship between these two clocks, and whatever be the other functioning, the flip-flop and other functioning, they're supposed to be synchronized with this particular relationship. So that becomes a synchronization of, means you're just synchronizing your circuit with respect to those two clocks. Now, if you cannot provide or you cannot figure out any relationship, like Aditya mentioned, two different sources, so two different PLL. So two different PLL is very difficult to come up with the relationship, direct relationship between those two clocks. So we consider them like, okay, these are two different clock sources, and they are asynchronous in nature. So in your design, what can happen, like this is the one thing, like in a top level and a block level. In a top level, let us suppose there is only one clock. Like in this particular case, the clock A and the clock C both are, let us suppose both are coming from outside from the different PLL sources. So you can say like, okay, these two are asynchronous clock. But when it comes to the clock A and the clock B, so clock B is basically generated through the clock A. So from the top level, I would say as a flat, if I will come up with the flat design, then I can easily figure out like, okay, clock A and the clock B both are synchronous in nature. They have a relationship generated with a certain digital block. But if I'm talking about a particular block, which is, let us suppose the top digital block and the bottom digital block, the middle one, two blocks. So some data is traveling from the top digital block, this particular block to the lower one. And for this particular block, the data is with respect to the clock A. For this particular block, the data is with respect to the clock B.
Okay.
Now, you don't know, because you're sitting inside this current design, you're sitting in this digital design, you don't know, like, okay, what is the relationship between the clock and the clock B. So on the block level, you can say, like, okay, whatever the data is coming, that data is coming with respect to a clock A. Whatever be the clock which is just triggering the flip-flops inside this digital block, that is with respect to the clock B. And for you, since you don't know, maybe as a constraint writer at the top level, I didn't provide you any information. So for you, within this block, this data and this clock, they are not synchronized with each other. So it's just like in a like where exactly you're sitting and what information you have. So if you have the relationship, if you can figure out, if you can ask the top level people, like, okay, I need a relationship between the clock A and the clock B, and the top level person will give you the relationship between the top and top B, that means it is very easy for you to design or just make the circuit inside this digital block. Else you have to consider things as a asynchronous, and you have to definitely, like Tilak said, you don't know the relationship, you don't know at what particular time which clock is going to trigger, or at which particular time you will receive the data. Then you cannot do the timing analysis around those timing analysis, basically mainly the setup and hold. You cannot check that particular part. But yes, in a asynchronous, like Aditya mentioned, there are a couple of other checks that is that anyways you have to do it. Like so timing checks doesn't mean only the setup and hold. Timing check, so this is basically for the tele, like timing check, doesn't mean it's only the setup and hold, but there are other checks also. So you have to do those checks, and that's the reason we are talking about this asynchronous and the synchronous clock, like how you're going to do that particular part.
Okay, so if everyone is clear up till this point, then the next thing which we wanted to cover is the idea of timing optimization during synthesis. Now, in this, our idea is to give you a brief introduction of what all will be covered, since each of these are a little bit in-depth topics and require some more understanding of the previous concepts, then we can explain them better. But here the idea is we'll give you a brief introduction of what all will be covered. You may or may not understand the terminologies completely in this topic. Just I wanted to let you know, because this is a later part of the course. So basically at the SOC level or at the top level, what we have usually is you have different blocks. There is a block A and it drives multiple blocks like block B, C, D. Okay, so first thing is, the first and foremost thing which is important to meet time, I would say, is someone to give you a good RTL. And even though this course is not about writing RTL, but we will introduce you to some good RTL practices, some resource sharing, some arithmetic optimization tricks, because those play an important role when you are analyzing the block during synthesis. You can do same logic by using if statements, but it can give you a way more complex netlist if you write the RTL slightly differently. So a general idea we would like to give you. So that part is from the RTL perspective. Next, what we will do is we will try to give you some things like, if you focus on this block A now, here first thing we are mentioning is the library optimization. Usually every tool vendor provides you a inbuilt library of tools, of designs. And what your synthesis tool does is it tries to read in that library. It tries to optimize and match your design from those building blocks and then size them from those building blocks directly. So that is the library based optimization part. and we'll try to explain you a little bit how the tool tries to do that. Next, it comes the test-ready synthesis. For this, we'll try to explain you what exactly test means. Here, we will be focusing primarily on the DFT, using scan. We'll give you an example of if you have a scan chain insertion, which is the most common DFT which is in the industry. Pretty much everyone does it, at least scan-based DFT. We will try to tell you how a synthesis tool tries to optimize your scan insertion, how it tries to take its timing into account, and by pre-analyzing the scan flops and other things. Okay. Then another thing which we would look at is, suppose we have a logic, when we usually have such logic where you have multiple flip-flops chained together with logic blocks in between. This is usually called pipelining, right? You have, that's how a typically digital design is done. You have logic blocks which you break down into multiple cycles, and you put flip-flops so that you capture timing after each and every operation so as to best meet timing. There are tricks in tools like register retiming, adaptive retiming, which we will dive into to show how they can help you meet your timing goals, and if you should be using them, when you should be using them, all those things. Not every one of these tricks, the optimization methods work every time. Not all of these are compatible with each other. So again, here we'll try to show you the trade-off space. That, as an engineer, I would again bring is very important to you. Understanding if we use this logic optimization or timing optimization, what am I gaining and what am I losing? Next, if you look, is this boundary optimization and auto ungrouping. This, what do I mean by this is, here we see that there is a clear hierarchy between a block A and block B. Whether, when I say hierarchy, the pins for block A would be defined, the pins for block B would be defined on its boundaries. Whether or not we want to enforce the fact that we maintain those pins, or the synthesis tool can combine these two blocks somehow and come up with a better netlist. And should we allow that, or could we allow that? Again, these are things which we will try to get into detail. So there are some things called boundary optimization, auto ungrouping, techniques in timing optimization, when we should use those. That is what we'll try to get into. Then what we usually notice is a block drives a lot of other blocks, a single pin. Then a technique which the tool uses is register replication. It multiplies the logics in multiple times, increases the drive strength to actually meet timing. So we use register replication sometimes, but it increases the area, it increases the loading on this pin. Game comes with its own trade-off. So we'll try to dive into this, when and where we should use this and how do we use this. Next one is, there are things like, do we prioritize the rise time, or do we prioritize the setup and hold time? And do we do the rise time enforcing on the clock network during synthesis, or we do not do this? Because during physical design, during the place and route, the clock network will be generated anyways. So that thing we try to both, again, doing that or not doing that has some trade-offs. Then user-defined path groups. Sometimes when you're not able to meet timing, you define your own path groups, optimize in those small path groups so that the tool does better optimization and analysis. So overall, that this is the bigger picture I want to give here is, we will try to capture the trade-off space, how we do these optimizations, when, where, and could we do these optimizations. That's the general idea behind synthesis timing optimization. At this point, again, I dove into a lot of information very quickly. Any questions would be welcome here. So I guess I'll ask a question. From the background you guys are coming in, Do you guys, how many of you understand the terminologies mentioned here, or these are new to you? You can just type new, or you know those terminologies, or you can speak. It would be valuable to us going forward with these lectures. As I mentioned, I don't want to dive into each and every detail here because these will come towards the later part of your lectures. You need to have some understanding of previous concepts to understand this. So some of you are saying that you know these concepts. That is good.
Yeah, actually, I'm new actually.
Okay. Yeah, even if you're new to these concepts, you should not worry. That's why I'm not diving into details on these concepts, because the previous information using of delay, constraints, and all those things need to be understood very clearly before you reach this stage and understand each of these things. But here, again, I am just, my perspective was that through this course, we'll teach you the whole trade-off space so you are able to make intelligent decisions as a design engineer, as any kind of engineer actually.
Okay.
Okay.
Yeah.
So our goal is not to give you one script and you just run that script and that is all. We will do that through the tool, but here you'll get to learn the whole trade-off and design space. That's the main goal. Okay.
Okay, sure.
Any other questions, thoughts? I think some of you guys are saying you know a few of them. That is good. Very good.
So like Ajay, you have asked one more thing, like how much practical and how much theoretical we will cover. So see, we are going to cover things from the tool perspective, but like I have mentioned with you individually also, like there are a lot of things from the fundamental point of view you should know. So when I'm saying the fundamental, that doesn't mean the theory, theoretical like in a bookish thing. When I'm saying the fundamental, I'm saying from the conceptual point of view, from the tool point of view, from the design point of view, uh, how things looks like, and like I've explained in the starting of the class itself, like whatever be our input output files, how the tool is going to use those input output files and is going to do the calculations, so that you can say like I just asked very clearly, like what is the meaning of the theoretical and the practical. So like if someone is saying like okay, that is a theoretical, you can consider that as a theoretical also, but that's a part of something which we are using day in day out, and that's a practical thing, because practically how the tool is going to read those information. Just 1 second. So that's a portion. Again, the subjective. Like if you know, then it can be a theoretical for you. But if you don't know it, it is a practical for you. So that's the way we are going to uh, do this particular course.
So there are
Anyone
multiple
else?
questions here which are saying, will we get to write constraints? How much constraints writing will we learn? So with respect to that, I can answer, we will give you multiple assignments on multiple constraint writing, and we will go over on them in class as well. So we're discussing them each and every, how do we write constraints for different issues. So that is one part which we are going to cover very thoroughly, constraint writing.
Okay, Sajid prefer to type. Okay,
Yeah,
Akash.
it's a
Yeah.
it's a really interactive session. But actually, I'm new only, means student only. So I'm just learning perspective. I'm dealing with this, and
Yes.
definitely I will ask questions also.
So that's more important for you basically, Akash. So it doesn't matter. So don't think like okay, whether it's a silly question, whether it is going to be very expert question. You just ask here. So the reason we have a mixed type of people, so that with the help of the questions which you're going to ask, maybe the people who are already in the industry, they are already working, they don't know. So it will help them to build their the basics and the fundamentals also. And there are a couple of questions which they are going to ask, and that's going to help you just to open your mind, like, okay, this is the industry perspective. So mostly in all of my classes or all of my courses, I usually try to keep the mixed audience, and it help in both the ways. And like I said, if at any point of it time it looks to me the question which you're asking, let us suppose you just ask any question related to the diesel thing or the CMOS related thing, and it looks to me it is very basic, then maybe we can have a separate session over the weekdays sometime, and maybe we can have a one slot where we will discuss that particular part. So that's, we can do any point of a time. That's not a big thing. And if you will ask such type of question, I can definitely within a 1 minute or the 2 minute, I will just brief you so that you can understand those slides and that particular topic. And then I will ask, then I will tell you like, okay, this is something which we can discuss offline. So this is for all the people who are new, and for them the certain terminology is new. So for everyone, things are going to be in that particular way. Okay.
Yeah. Yeah. Sure. Thanks.
Okay. Okay. Thanks a lot. Bye bye. Bye everyone.